So before we get into any of like the gas laws and diffusions and stuff, I just want to ask each and all of you just like a question. What makes a molecule a gas molecule? Well, actually, before you answer this question, I also want you to consider this as well. So if there was one molecule of water in a vacuum, right, and the temperature was below freezing, would you consider that molecule to be an ice molecule or solid water? If the temperature was, above freezing, would you consider that molecule to be a liquid water? Does the property of the molecule itself change when the phase of the substance change? Anyone have any answers? Well, you could probably answer my first question to what makes a molecule a gas molecule. Does anyone have any ideas? Okay, so if you're, well, although nobody really answered the question, basically, high temp, low temperature. Well, yes, intermolecular forces. You are absolutely correct. The lack of intermolecular forces is exactly why it makes a gas molecule. Yeah, so give yourself a pat in the back. So basically, substance of a phase like solids, liquids, and gases, they only exist because of the collective attractions between molecules, basically intermolecular forces. Gases, liquids, and solids are what chemists call bulk matter, which is basically molecules in extremely large quantities, countless quantities, whatever adjective you want to put it in. But basically, so phases only exist because of the collective behavior, intermolecular forces in this case, of huge numbers of individual molecules. So this might not make sense right now, but for other things like pressure, you'll soon realize that a lot of things you observe, like phases or, again, pressure, occur because of the collective behavior of individual molecules, in this case, intermolecular forces. So this is like an example of macroscopic level versus microscopic level in chemistry. It's a very common concept that we use in chemistry. And I will make sure to explain this much better later, but you should never assume that a macroscopic property is also observed in the microscopic level. What I mean by that is well, here's an example for people who've taken physics before. If you study classical mechanics or Newtonian mechanics, and scientists from the 1920s tried to apply classical mechanics to microscopic objects like atoms or subatomic particles, they realized that, well, it didn't work. Which is why we now have quantum mechanics, which kind of correctly assumes, correctly makes the calculations for microscopic properties. So if you don't really understand what I just said, don't worry about it. It's probably not going to be on the test, but I'm just trying to help give you a foundational understanding for this one. So I mentioned about intermolecular forces, so I'll cover that briefly as well. So basically, they are attractive forces between two molecules, right? And they lower the potential energy of both the molecules. In other words, it makes them more stable or in a lower energy state, which is something every molecule wants to be in. They are weaker than normal bonds because the distance between the two molecules is often much greater than something like covalent or ionic bonding, but also the charges of the two molecules are only partial, or sometimes they don't even exist, like London dispersion forces. So they're just much weaker in general because of those two reasons. But because there are millions, billions, trillions of intermolecular forces between molecules, again, coming to the bulk matter thing, it can often hold molecules together. So one question you might have is, well, why do liquids and gases exist if the intermolecular bonds holds the molecules together? Right. Well, and I will prove this as well later, but all molecules have some kinetic energy, and that kinetic energy is related to temperature. And so as temperature increases, the kinetic energy of these molecules increase as well. If you don't know any physics yet, then you can just consider it that like they move much more faster or vibrate faster depending on the phase. If the kinetic energy of each molecule is sufficient enough to overcome the intermolecular forces, or basically, if the kinetic energy of each molecule is like too strong for the intermolecular forces between them to hold molecules together, that's when the molecules start to overcome intermolecular forces and move and become a liquid or gas or whatever. And that's why, as you increase temperature, a solid becomes a liquid and a liquid becomes a gas. Cool. Does anyone have questions? That was like a lot of content. Okay, stock, I guess, sure. So we can talk about the property of gases. This is the stuff that actually matters. So, like I said, in chemistry, there's a lot of things that are considered from a macroscopic level and a microscopic level. And let's start with compressibility. Gases are compressible, and this is something from a macroscopic level. For example, let's say you have like a syringe, right? And if you block the entrance of the syringe and try to push on it, you'll realize that you can, to some extent, you can compress the air inside the syringe. You know? Yeah. So basically, because gas molecules are not bounded by intermolecular forces, the distance between these gas molecules are great. Like the distance between them are much, much greater than something like a liquid or solid because, well, they have a lot of kinetic energy, enough kinetic energy to not be bounded by intermolecular forces. They're fast and therefore they're scattered around much, much more than liquids and solids. So if you apply an external force to the container, basically if you shrink the volume or try to shrink the volume by putting pressure onto the container, then you'll soon realize that it can much easily compress the substance into a smaller volume, unlike solids or liquids, where basically if you try to compress it, it barely compresses at all because when you compress something like a liquid or a solid, because they are bounded by intermolecular forces, if they get too close, then repulsions start to kick in, and then, well, you can't really compress it. So that's something you have to keep in mind. So another property of gases are that gas molecules are chaotic and random. This is looking from a microscopic perspective or a microscopic level. Again, gas molecules have a lot of kinetic energy. They're fast, they're random, they're chaotic, they like to collide a lot. Typical. So the last one I want to talk about is pressure. And pressure is basically over a certain area of a surface, the collective forces applied by the individual gas molecules to a substance is the same. Basically, the amount of force that is applied in a certain area is homogeneous. Like all chemists, I don't know. I'm not sure if all chemists would say that pressure is homogeneous, but basically, the example I would like to use is that if you're on sea level, the atmospheric pressure is constant, almost constant throughout, right? Like wherever you are on Earth, the atmospheric pressure is constant at sea level, and that's true. And this is because the collective collisions between the wall and an enormous amount of molecules over is, a lot. Oh, and I would like to know, wait, never mind. So does anyone have any questions? Okay, I will continue then. Okay, everything from here is just uphill. It's very simple. Does anyone not know how to measure pressure with a barometer or a manometer? Should I cover this? Please raise your hand. Okay, hold on. Let me get a drink. So for the case of a barometer, this was how scientists basically figured out what the atmospheric pressure was. We used in the old days, people used mercury metal because it's dense. You know, if you think of a metal, you think of it as something like a dense material, unless it's like aluminum or beryllium, whatever. But anyways, basically, I said that for pressure, it is basically a collective force applied to a given surface, right? So if there's gas molecules like here, that somehow, well, not somehow, but they randomly collide with the surface, the mercury metal here, they are applying pressure to this mercury metal. Therefore, if you apply pressure on both of these sides, there's no way for the mercury to go except inside these tubes, correct? Right. So the greater the atmospheric pressure, the higher this will go up. And the lower the pressure is, well, because of gravity and because the mercury metal inside this tube has a tendency to fall back down, well, it's going to have a lower height. Now, how do we actually measure the pressure inside these tubes? Well, you might remember from your general chemistry class that of this equation. That is not what I wanted. Of this equation, VGH equals pressure. Give me 1 second. So, and I will derive this equation just for fun. So, the pressure equation was P equals force over the area that is relevant, correct? And if the Earth's gravity, like I said here, and I'm so sorry if you're not taking physics, but I hope this somewhat makes sense. Because there is a gravitational force going downwards here, this force is basically mg, or equal to mg. The area, well, no, the density of a substance, in this case, the density of mercury metal here is defined as the mass divided by volume, correct? E equals m over v. If we arrange this definition to m equals dv and substitute this into this equation, we get that dvg over a. Now, what is volume over area? It's height, right? So we get our equation dHg, which calculates the pressure of the atmosphere. All right. But you know, nobody really cares about the barometer, so we'll go with the manometer next. So in the case of the manometer, it's basically the same concept, except instead of it being in the atmosphere, it's actually in a tube. If this is closed, then you're basically, the manometer is a device that compares two pressures of different regions. For this first example, this is what we call a closed manometer. And you're basically comparing the pressure of this gas with a vacuum. So whatever pressure this gas exerts, then this height difference between the vacuum and the gas is basically the pressure of the gas. So, for example, let's say that, oh, I don't know, this difference was like 600 millimeters of mercury. Then the pressure would be 600 millimeters of mercury. Now, the next two examples on your right is what we call an open manometer. It's comparing the pressure of a gas with the pressure of the atmosphere, or really, it could be another gas, really. And by doing this, this exerts a certain pressure, and the atmosphere also exerts a certain pressure, 1 atm. Then the height difference will basically signify the difference in pressure between the gas and the atmosphere. So if the atmosphere, if the height of the atmosphere, let's say here, is lower than the height of the gas, that means the atmosphere is applying much more pressure than the atmosphere of the pressure of the gas. Therefore, we get this equation, where pressure of the gas is practically the pressure of the atmosphere minus the height difference here. This one is in a... Wait, this is literally the... Oh, never mind. So if the pressure of the gas is lower, or like how much pressure the gas is exerting is greater than how much pressure the atmosphere is applying. Because the pressure is much greater in the gas, that means P gas equals P atm plus HPG. P is density, just in case you're confused. All right, does that make any sense? I know that was a very crappy explanation, but does anyone have any further questions about how to measure pressure? Now, in HPG, P is basically density. P is equal to D. P is how physicists, like people studying physics, like to label density. So just use HDG. Does that answer your question? Cool. How do you get density? Well, that'll be given to you. It's like there are many ways to measure density, but you won't ever have to actually calculate it. Yeah. All right. So units. I have no idea why, but chemists like to use a ton of units for gas measuring pressure. There's Pascal, standard pressure, atmospheric pressure, millimeters of mercury, torr. Honestly, my favorite is atmospheric pressure, but I'll just briefly go over these. Pascal is the SI unit for pressure. I don't think you have to know that, but you should know that standard pressure, or 1 bar, is equal to 10 to the 5th pascals, or 100 kilopascals. And the most important conversions are actually these two, atmospheric pressure and millimeters of mercury. So for atmospheric pressure, or the pressure at sea level, that is equal to 101.325 kilopascals. You need to memorize this like conversion because it will always show up in the exam. Like, not directly, not explicitly, but you will have to use these conversions in some question. Same for millimeters of mercury. This unit was only created because of the whole, mercury barometer thing that nobody really cares about anymore. 760 millimeters of mercury equals 1 atm, which also equals 101.325 kilopascals. And torr, nobody really cares about torr. It's just, the same thing as millimeters of mercury, but there's some trivial difference between it. You don't need to use torr. Nobody cares about torr. All right. Next, let's talk about the gas laws. Very exciting stuff. So Boyle's law, Charles' law, Gay-Lussac's law, Avogadro's principle, and ideal gas law. I'm sure you've all heard of them at least once learning general chemistry. Boyle's law basically says that pressure and volume is proportional to each other. Charles' law states that volume is indirectly proportional to temperature. Gay-Lussac says, well, pressure is indirectly proportional to temperature. Avogadro's principle basically says that the molar volume times the moles of gas is always equal to volume. And then the ideal gas law, classic PV equals nRT. I'm sure you've all heard of it and you use it religiously because you will most definitely need to use it for your upcoming Unit 2 exam. So one thing I will like to emphasize here is something called extrapolation. It is basically estimating the dependent variable using a relationship. In this case, it would be for Charles' law and Gay-Lussac's law. I don't know how to pronounce that properly. Don't mind me. It's typical stuff. Here's the thing. Why do we use extrapolation? The only reason for it is because in most cases, real gases or gases in nature, like hydrogen gas or helium, oxygen, nitrogen, these kind of real gases, they tend to liquefy below a certain temperature, at very low temperatures, basically. And since we can't really get experimental data below these temperatures, what we're doing is we're basically estimating. We're estimating what the volume would be at like this very low temperature or something like that. And also, another thing you have to keep in mind is that you cannot reach 0 Kelvin. 0 Kelvin, basically absolute zero. You can never reach absolute zero. Or there has been like some experiments where they've gone like very, very close to absolute zero, but if you look at something like Charles' law, you can see that if T equals 0, then volume equals 0, which makes no sense, right? So it's crucial for you to, and I'm pretty sure Pulik will ask you this on the exam, it's very crucial for you to draw the graph to be like this. For example, for Charles' law, you can't start from 0 because you can't get the data for it. You have to start with something, you have to start with this. Oh, okay, what? Yeah. So basically, you have to start from some volume. Because theoretically, you can't have 0 volume, or at least in chemistry, you can't. Does that make sense? Oh, and also, you should probably kind of know why these graphs exist. I'm sure, you know, you're aware of these graphs and I don't have to explain them. All good? Can we get like a smiley face or an agree, reaction, feedback? Yeah. All right, cool. Sorry. So, applications of the gas law. This may or may not, you may or may not have to use this for your exam. I don't really remember, but I'm pretty sure you do. So these 3 equations, very useful. You can measure, so with the ideal gas law, just by rearranging it, you can measure the molar volume of an ideal gas. You can measure the density of an ideal gas. You can even measure the molar concentration of a gas. So what is, well, let's start with molar volume. What is molar volume? Well, molar volume is basically volume of the gas over moles. So if you remember 22.42 from your stoichiometry things, yeah, that's molar volume at a certain temperature. So you know that PV equals nRT. If we rearrange this, we get nRT over P. And if we plug this in here, we can cancel these out and we get RT over P. This is your first equation that you should probably not memorize, but know how to derive. Density of an ideal gas. This is also something very common that you would use. Density is mass over volume. And mass is basically the number of moles times molar mass, correct? Or molar mass of the gas. So that would be NMR. And then the volume is basically, well, we basically use this equation and plug it in here. So V equals NVM, correct? And then we can cancel these out, and then we know that VM equals RT over P. If we plug this in here, we get MRP over RT. This is your second equation. The last one, the last equation you probably should know how to derive is the molar concentration of a gas. Similar to something like a solution concentration, but except instead of dissolving in water, you're dissolving in nothing. That made no sense. Okay. Concentration is moles over volume. If you rearrange PV equals nRT in terms of N, then you get PV over RT. If you plug that in here, and then not rearrange it, if you cancel volume out, you get P over RT, which is I was going to use, I can't pronounce things today. P over RT is basically the inverse of RT over P, so it's 1 over molar volume. You know, some trivial stuff you can memorize if you want, but very cool. All right, any questions? Partial pressure and mole fraction. All right. So Dalton's law of partial pressures is also definitely something you need to know. It basically states the total pressure of a mixture of gases is the sum of the partial pressures of its components. Let me repeat that again. The total pressure of a mixture of gases is the sum of the partial pressures of its components. That being said, a mixture of gases that do not react with one another behaves like a single pure gas. So here I've given you 2 forms of the equation. Honestly, I like the second one better because, well, I'm bad at math and I feel like the first one is much more complicated than the second one. So, and then there's also mole fraction. Mole fraction is basically like the percent composition of a gas in moles. Okay. And it's used in other things like binary liquids and liquid mixtures as well, but you'll learn that soon. And you can use mole fractions to, you can use mole fractions to prove like Dalton's law of partial pressures. Basically, if we say that there are 2 types of gases, gas A and gas B, because mole fraction is basically like not really percent composition, because if you add up all the mole fractions, it has to equal 1. So basically, it would be percent composition, except you don't multiply it by 100. Right. So if you said that like gas A had 0.8 mole fraction, and then gas B had 0.2 mole fraction, and if you plug these in and then got the pressure of each of them, then you'll realize that it's basically the same as, it's basically the pressure exerted, Does that make sense? Okay, cool. The Diffusion and effusion. All right. This is something that a lot of people tend to ignore the importance of, so I'll just emphasize it here right now. So diffusion is basically, the gradual dispersal of one substance through another substance. So this another substance, for example, can be air, and this one substance can be like vinegar. A bottle of vinegar gradually dispersing its pungent smell when it's open. I remember Gilman and Kulik both used this example in their classes. Diffusion is basically the escape of a gas through a small hole into a vacuum or region of lower pressure. An example of this can be something like air escaping from a bicycle tire valve. So if you have like a tire like this, the gas molecules here are high in pressure. So if there's a small hole here, then some gas molecules will be able to go out of this hole while others just bounce back and forth with the walls. It's just because why this occurs is because at higher pressures, because they are colliding much more with the surface of the walls, that means they have a much more higher probability of getting out through that hole. Basically, I think that made total sense. All right. So the importance of effusion is that, well, there are two experiments that Graham, the person who found out about the law of effusion, made. And the first experiment that he made was that at constant temperature, the rate of effusion is inversely proportional to the square root of molar mass. Basically, rate of okay. So rate is basically inversely proportional to the square root of molar mass. Sick. Okay, the second experiment that Graham figured out was that effusions at different temperatures reveal that the rate of effusion is proportional to the square root of temperature. This is something that people don't really talk about, and it's very important. Why? Because just from this experiment, we have just figured out that temperature is indeed related to the rate of effusion, and like I said, the rate of effusion basically is the same thing as the average velocity of these molecules, these gas molecules. So the higher the temperature, the higher the effusion. And because there's higher effusion, that means, well, there's higher kinetic energy, or higher average kinetic energy, higher velocity, whatever. Because there's higher velocity, they collide more with the walls, and they have a higher probability of getting out through that small hole. Yes. So this is where they figured out how the average speed of gas molecules is proportional to the square root of temperature over molar mass, this right here. And this is very important. But really, honestly, in the Unit 2 exam, the only thing you really need to know about is this equation. Rate of effusion of A molecules over rate of effusion of B molecules equals square root MB over MA, because the rate of effusion is inversely proportional to the square root of molar mass. All right. Does anyone have any questions to that segment? I'll take that as a no. All right. KMT, or kinetic molecular theory. All right. So basically, the ideal gas law and the ideal gas model itself, well, it's a model. And what does a model try to do? A model tries to predict what actually occurs in the real world. Whether that happens to be accurate or not depends on whether, well, it depends on how many things it ignores that happens in the real world. What I mean is that, well, a model tends to simplify many things that occur in the real world because, well, they're a real pain to deal with. And I'll explain what the ideal gas law doesn't take into consideration of later. So often, these models tend to be fairly accurate as long as you take into consideration of its limitations. So if you see the KMT right here, oh, I think I forgot to, I'm not sure if I said this, but the ideal gas equation is derived through just those 5 rules. Just by having those 5 rules, using like a bunch of physics and stuff like that, that's how they derive the ideal gas equation. All right, so from the KMT, I know the rules sound really weird and really confusing, but the only thing you have to consider is first, rule number 1, the volume of gas molecules are negligible. This just means that the ideal gas model does not take into consideration a volume of gas molecules. Now, rule number 4, the molecules do not influence one another except during collisions. This basically means that the ideal gas model does not take into consideration of intermolecular forces. Okay. Now, the rest of the rules, or rules 2, 3, and 5, these are just physics stuff, but all you have to know is that the ideal gas model does not take into consideration of relativistic effects, which basically means like quantum mechanics. Remember how I said about macroscopic and microscopic levels in chemistry? This is kind of like that. Basically, the ideal gas model tried to apply macroscopic concepts like Newtonian mechanics, classical mechanics, into microscopic, and therefore it does kind of deviate from the real situation. But honestly, what makes the biggest impact are the two conditions that we ignored above: the volume and the intermolecular forces. So now here comes the actual like important stuff. So the limitations of the ideal gas model. The ideal gas law is what we like to call a limiting law. Basically, the ideal gas resembles a real gas, like a gas in real life, you know, hydrogen gas, helium, as the pressure of the gas approaches 0. Or more formally, we would say something like the ideal gas resembles a real gas, or no, sorry, let me reiterate. Basically, the ideal gas model becomes more and more valid as the pressure of the gas approaches 0. Now, why is this true? It's because the separation between gas molecules are so great that you can ignore basically collisions between molecules and the possible intermolecular forces between the molecules, because the distance is so great. It's just that intermolecular forces become negligible when distances are so great, or, you know, I hope you get the point. All right. But it also resembles a real gas as the temperature of the ideal gas increases. Why is this? Well, as I keep saying, as temperature increases, the average kinetic energy of gas molecules increase, right? And as the kinetic energy of these molecules increase, that means you have much, much more energy to overcome the intermolecular forces between the molecules, to the point where, you know, they're just not much affected by them anymore. Once the temperature is so high, that their kinetic energy is so high that the energy lowered just by intermolecular forces is just like negligible. So basically, on this slide, all you have to take from the slide is, as temperature increases and as pressure decreases, the ideal gas law becomes more and more correct. Does that make any sense? Any questions? Okay. All right. Moving on. KMT equations. So, from the kinetic molecular theory, you can derive this equation that you see over here. Now, I would derive this equation because Jülich isn't here and I can do whatever I want, but it has a lot of physics involved and I don't want to use too much of it in this session. So just know that with kinetic molecular theory, you can derive this equation. And by rearranging this equation, we can get very interesting equations just from this one equation. The first one we want to look at is the relationship between temperature and velocity, or the root mean square velocity. And I know root mean square sounds really complicated, and to be honest, it kind of is, but just think of it as like, you know, another type of average of velocity or something like that. Okay, so we know that PV equals nRT. If we plug in nRT here, we get nRT equals 1/3 n molar mass and then V squared, correct? We can cancel the n's, and if we divide both sides by t, we get this equation. And what does this equation tell? Well, it gives you a relationship between temperature and, well, velocity. That's all you need to know. And it's very important because I talked about how, you know, as temperature increases, kinetic energy increases. Yeah. All right. So the second equation is basically a rearrangement of the first equation, except it's solved for the root mean squared velocity instead of temperature. Now, this third equation is more interesting because, well, if you remember from your physics class, you should know that the kinetic energy is equal to 1/2 mv squared, right? Doesn't this relationship seem very, you know, doesn't this seem very similar to something like this? And this seems very similar to m/r. Basically, what I'm trying to say is that this is derived from this, or it's basically somewhat of a rearrangement of this. And we can finally justify that as you increase the temperature of the system, the gas molecules increase, the kinetic energy of gas molecules increase with temperature. Does that make any sense? Also, if you're curious about like how the whole thing is derived for the equation above, then shoot me an email and I'll give you a review. I can't speak today. All right. Anyways, just shoot me an email if you're interested. Any questions? We're running out of time, so I'll try to be quick. Okay, so a brief explanation using the empirical laws. I mean, the brief. I can't speak English today. All right, so let me give a brief explanation for the empirical laws using KMT. Okay, so for Boyle's law, as you decrease the volume, the number of molecules in a given region increases, correct? And if a number of molecules in a given region increases, then you would expect more and more collisions because, you know, the walls are much more closer to you, correct? And therefore, because the collective forces of the molecules applied to a given surface increases, we can justify that pressure increases, correct? Okay, and the same thing basically goes for Charles' law. As temperature increases, the average speed of a molecule increases. And because there are more collisions with the wall, pressure increases. And increase of pressure is, well, counteracted by volume. So the volume increases. Does that make sense? And Avogadro's principle, as number of molecules increase, the volume increases in order to account for the pressure of the gas to remain constant, correct? What does B stand for? B stands for a constant. So in honors chemistry, you probably recall using something like P1V1 equals P2V2, right? Basically, it's the same thing. P1V1 equals some kind of constant, and this constant also equals P2V2. That's how the relationship is justified. Can you explain Charles' law one more time? Sure. So as temperature increases, the average speed of the molecule increases. The kinetic energy increases basically. And I'm confused about how volume increases. Oh, okay. So I think I should emphasize that for Charles' law, in order for Charles' law to be true, the pressure of the two environments has to be constant. And the number of molecules involved also has to be constant. Those are two variables that has to be constant in order for Charles' law to be true. Does that make sense? So when I said that the average speed of the molecule increases, then because there are more collisions with the wall, you would assume that pressure would increase, right? But because pressure is constant, the increase of pressure is counteracted by volume. Basically, the volume increases to make sure that the pressure is constant. Does that make sense? Okay, cool. Next slide. Maxwell distribution of speeds. So although pressure is homogeneous, this does not mean that the force applied by an individual molecule, or basically like the velocity of an individual molecule, is the same. What does that mean? Well, that means that each gas molecule can have very, very different velocities, traveling at very, very different speeds, basically. And the Maxwell distribution uses the kinetic molecular theory to predict this distribution of the velocities of gas molecules at a certain temperature. And from these two graphs, from this first graph you see on the left, you can see 4 different gases, noble gases that were used in the experiment. As you can see, xenon is the heaviest and it has the smallest interval. Basically, the smaller the interval, the more similar the velocities of 2 xenon molecules are. Basically, they all tend to have very similar speeds. The standard deviation is small. Whatever explanation you like. And for something very light like helium wides fairly in speeds. It has a wide interval. So one helium molecule can be 250 meters per second. One can be 2,300 meters per second. It has a wide interval. So basically, from this result, you can come up with the conclusion that lighter molecules have higher average speeds, but also wider intervals. Because from Graham's law of effusion, we've learned the relationship between, molar mass and effusion, right? And I explained how effusion relates to basically average velocity. And the same thing goes for temperature. As temperature increases, the average molecular speed increases as expected from the equation EK average equals 3/2 RT. You would expect that, but the interval also becomes wider. Why? Well, because that's how gas molecules work. All right. Any questions? This is the end of section 2. So if you have any questions about gas laws or any of the topics we covered, this is your time, because we will, for the next 30 minutes, solve some problems. If you're good, can you give me like a smiley face, check mark, whatever? All right.